Alright, so we talked a little bit last time about cyclohexane, which is a nice simple ring molecule. It's very common to have six-membered rings in organic chemistry, many times saturated, so they're all single bonds like cyclohexane. And so understanding the rings and how things can be attached to the ring is very important for an organic chemist. We're going to talk about three different types of isomerism with substituted cyclohexanes, and we're going to focus on a very small set of things where we talk about disubstituted, or where we have two substituents and a cyclohexane ring not on the same carbon. So again, very restricted discussion. One of the first things to understand is we can have constitutional isomers where the substituents sit on different carbons relative to each other. So let me read what this says. It says cycloalkane isomers, and cycloalkanes restrict the motion of substituents so that they're either going to be on one side of the ring or the other. No rotation around single bonds, nothing short of breaking bonds, is going to cause a substituent to go from on top of the ring to below the ring if that's where they are. For instance, for 1,2-dimethyl cyclohexane, the substituents, the two methyl groups, are either going to be cis, meaning they're on the same side of the ring, or trans, meaning they're on opposite sides of the ring. So the first part is the constitutional isomerism here, that when it says 1,2-dimethyl cyclohexane, the two substituents, the two methyl groups, are on different carbons that are next to each other. So if we just looked at a typical cyclohexane ring in the chair conformation, and you should definitely practice drawing these guys. I usually would start with two parallel lines and then connect up the head and the foot of the chair. Now I draw it a little more fluent because I've been doing it for a while. And so what I'm saying is, if you had this axial position above the ring was a methyl, then regardless of what happened with the ring, this methyl would stay above the ring. And that's the first position, or carbon number 1. Then if you walked around the ring numbering the carbons, you could see that carbon number 2 is adjacent to carbon number 1, which makes sense. On the number line, 1 and 2 are adjacent. Carbon number 1 would be adjacent to carbon number 2. So if I put the other methyl group in an axial position on carbon number 2, then carbon number 1's methyl would be on the top side of the ring, and carbon number 2's methyl would be on the bottom side of the ring. So this would be an example of 1,2 dimethyl cyclohexane. And now we're getting pretty complicated because the ane means we have just single bonds. Hex means we have 6 carbons. Cyclo means it's in a ring, so each piece of the word means something. Dimethyl means we have 2 methyl groups substituting for hydrogens in the cyclohexane, and then 1 and 2 means that if one of the methyls is on carbon number 1, the other one is on carbon number 2, or adjacent to that. So the constitutional part is where the methyls are attached, constitutional isomerism. And so these guys being on adjacent carbons is different than if it was 1,4 substituted and they were on carbons on opposite sides of the ring. So now what we're adding in here is the language that was just described here on this slide. If you have 2 methyl groups substituted on a cyclohexane, these substituents can either be on the same side of the ring or opposite sides of the ring. And different 1,2-dimethyl cyclohexanes are going to be different because of this feature. So I went ahead and drew a dimethyl cyclohexane, 1,2-dimethyl cyclohexane, with one of the methyls on the top side of the ring and the other on the bottom side of the ring. And so that would be trans 1,2-dimethyl cyclohexane, because the methyls are on opposite sides of the ring. One's on the top, one's on the bottom. Now where the conformational isomers come in is that because of rotations around single bonds, the axial position can move to an equatorial position, and the equatorial positions can move into axial positions. So if I did a little twisting and turning around the single bonds, I could get this molecule to adopt a new sort of geometry where now the methyl that was in an axial position will now be in an equatorial position, but it'll still be on top of the ring. And then the methyl here that was in an axial position will move to an equatorial position. Again, this is carbon 1, carbon 2. One methyl's on top of the ring, one's on bottom of the ring, but the conformational isomers, so a conformational change means that axial positions move to equatorial positions and equatorial positions move to axial positions. So this other guy here is also trans 1,2-dimethyl cyclohexane, but this is going to be the lower energy one, the lower energy conformer, because the equatorial positions are roomier. That's something in the cyclohexane video I talked about, how axial positions are crowded near other axial positions, even though it doesn't look like it in the drawing. This methyl is sort of bumping into this hydrogen, whereas this methyl in an equatorial position is very far away from just about anything else in the molecule. So that's going to mean lower in energy when both large substituents are in equatorial positions. In this one, both large substituents are in axial positions. So these are the two conformers, or two conformational isomers of the trans 1,2-dimethyl cyclohexane. One has both axial positions, the other one has both equatorial positions, and you might be asking yourself, is there any way to have one axial and one equatorial? And that's certainly the case, and if you start thinking about the variety of possibilities and what you can or can't have, it might be worth trying to draw that out. So let me go ahead and just start with a new cyclohexane ring. Dogs are very excited about this. They love their organic chemistry and love learning new things. But if I put this guy in an axial position above the ring, right, and I want to put the other substituent on an adjacent carbon also above the ring, then it's going to be in an equatorial position. And at first, when you're first trying to do this, it might be useful to draw out your chair form with all of the axial and all of the equatorial positions, because where they're located is really important. Like this, if you have an axial position pointing up, the equatorial position is going to be pointed slightly down. So the ones that are above the rings are going to be, I'll put little asterisks for the ones that are above the ring, are going to alternate axial and equatorial. As you walk around the ring, your axial and equatorial positions above the ring are going to alternate. And that's something that building the molecule, drawing the structures several times and thinking through it So if you wanted these guys, the two methyl groups, to be cis 1,2-dimethyl cyclohexane, then you've got to have one axial and one equatorial. So this one is going to be sort of a medium energy, or the middle energy one, because equatorial ones are lower in energy, axial positions are higher in energy, so 2 axial highest energy, 2 equatorial lowest energy. This one is going to be 1 axial, 1 equatorial, so that's sort of the middle energy isomer as we work through the different possibilities.